Hello! I believe I owe you some more examples of finding area, maybe other stuff, using parametric curves, or a curve expressed parametrically. Let's do a couple examples. Why? No, I don't want standard, I want pen, I want format. You're not writing? Oh, jeez. This happened last time. If I find a new node, will you write? Okay. Let's do an example. Let's do one that we know. Let's do x equals r cosine theta. Actually, let's pick an r. Let's make r 3. Let's let x be 3 cosine theta. Let's let y be 3 sine theta. Hopefully we took a pre-calc class and we know this is parametric. This is the standard parametrization of a circle of radius 3. To catch the entire circle, we would want to go from theta equals 0 to theta equals 2 pi. And I know some things about sine and cosine. I know that sine looks like this. It increases and then decreases. I know that cosine looks like this. It decreases, then it increases. They both have a cycle of 2 pi. Yeah. Let's think about what happens if I try using the integral of y dx. It's supposed to give the area. I mostly, like, the idea is, what do I get if I just integrate from 0 to 2 pi of y dx? Is it going to give me the right thing? Sometimes this stuff's going to be negative, and sometimes it's going to be positive. Very often, just integrating y dx from here to here gives you the right thing, maybe with a minus sign on it. Let's think about what happens as I break this into pieces, though. The key pieces are, when is this positive? And when is dx, meaning dx dt, when is this positive and negative? So let's try thinking about that. Dx is the derivative of x. In this case, y is 3 sine theta. I know it is positive up until pi. And I know y is negative after there, from pi to 2 pi. X is 3 cosine theta. So dx dt, or dx is negative 3 sine theta dt. Hey, dx happens to behave the exact opposite. Dx is negative here, from 0 to pi. Dx is positive between pi and 2 pi. So no matter what, the integral of y dx is always giving me something negative the entire time. What am I going to get for those times? From 0 to pi, y is this positive amount. So I'm going to get the area up below the curve and above the x-axis if I integrate y dx. But dx is negative. Why is dx negative? Because my x quantities are going from x equals 1 to x equals negative 1. My x quantity is decreasing. Dx is the change in x is negative at every step of the way. So I'm going to get that area integrated against a negative differential. I'm going to end up with a negative number, as if I had integrated from 1 to negative 1 instead of integrating from negative 1 to 1. So the integral from 0 to 2 pi y of t, or the integral from 0 to pi y of t dx dt is going to give us this area, but negative. And keeping track of the fact that it's negative because my y is giving me a positive, my dx is giving me a negative. What happens if I integrate from pi to 2 pi? This is going to give me, from here to here, along this part, y is negative. So I'm getting, just like when you integrate a negative function, you get negative values. I'm going to get this area but negative because it's below the x-axis. But my dx is positive. So I'm not getting a weird negative thing here. So I'm going to end up with this area, but negative. And the key thing I'm keeping out for is if I just combine those two together, the integral from 0 to 2 pi is going to add up to be the entire circle, but negative. The key thing I'm looking out for is the things aren't canceling each other out. They are stacking together and building the right thing. Before double checking that, for all I knew, I was going to get this thing positive and then get this thing negative, and they'll come out to be 0 or some other cancellation that I don't want to happen. I think you need to manually inspect it and verify that you're getting the same orientation for both of them, and then afterwards it's negative, so you can fix it. Well, what do I get when I integral from 0 to 2 pi of y dx? I'm integrating from 0 to 2 pi. Y was 3 sine theta. Dx was negative 3 sine theta. So I'm getting d theta. So I'm getting negative 9 integral 0 to 2 pi of sine squared theta. How do you integrate that? You integrate sine squared using that trig identity, negative 9 integral 0 to 2 pi. It's 1 minus cosine 2 theta over 2. Let's move the over 2 outside. I have negative 9 halves, integral from 0 to 2 pi of 1 minus cosine 2 theta d theta. Should have been a d theta here. It's negative 9 halves, integral of 1 is theta, integral of cosine 2 theta is sine 2 theta over 2. I want to evaluate that from 0 to 2 pi. I get negative 9 halves of 2 pi minus 0 minus 0 minus 0. So I get negative 9 pi. And the area of the circle is 9 pi, because I knew this was going to give me my negative answer. I believe there's a general principle that if you have a closed loop and you integrate from a starting point to an end point, you will get the area inside that curve, and it will be negative if you went clockwise around, and it'll be positive if you went counterclockwise around. I think that's a thing you study more deeply in Cal 3. It's a theorem. I haven't taught Cal 3 in forever, so I don't know this off the top of my head. But that tends to be, in my experience doing problems like this, how this works out. Let's try another example where it's even harder to graph what's going on. Let's sketch. I'm making a problem up now off the top of my head, so this is how things go wrong sometimes. I want to sketch x equals t cubed 1 minus t, and y is t 1 minus t cubed? Yeah, let's just go with cubed. This is a parametric thing. This is a hard problem to understand. I guess first off I want to think about what do the graphs of each of these things like. I'd like to understand their intercepts. Those are going to be intercepts for my parametric curve when x equals 0 or when y equals 0 is when it crosses the x or y axis. If I understand those, I can maybe get a good graph. Like in between, I know it'll be what quadrant it's in at least. And I'd like to know when their extreme values are. When does x have a maximum? If my parametric curve looks like this is a place where x has its maximum. That's going to be helpful to understand because that's when dx switches between being positive and negative also. And over here is where y has a max. So I'd like to understand both of those things. When are the x's and y's increasing, decreasing, positive, negative? That's like a bare minimum to come up with a decent parametric sketch of this. What does x look like? Well, both of these things have x-intercepts at 0 and 1. because they both have a factor of t and they both have a factor of 1 minus t. They're both positive in between. What are they doing in between? What does t cubed 1 minus t look like? Let's take a derivative. Derivative of this using the product rule is 3t squared 1 minus t, plus this time leave the first part alone, derivative of the second. I can factor out a t squared, and I'm left with 3 minus 3t minus another t. That's t squared 3 minus 4t. When do you equal 0? You equal 0 at t equals 0, and you equal 0 when 3 minus 4t equals 0. That's at t equals 3/4. I can solve that one in my head. So that's when the derivative of x equals 0. I know we pass through this point. I know we have a horizontal intercept here. And I know you have a local, I guess, judging from the fact that I know that you're positive in between, I can surmise that it must be a local max at 3/4. So something like that. What happens if I plug in a negative number? 1 minus a negative will be positive, a negative cubed will be negative, so I'm going to do something like this. My graph of x looks like that. What's my y graph look like? Again, it equals 0 at 0 and 1. My formula is y equals t1 minus t cubed. I can take the derivative and get derivative of the first, leave the second part alone, plus leave the first part alone, derivative of the second. Factor out two 1 minus t's, 1 minus t squared times what's left inside, 1 minus t minus 3t. So I get 1 minus t squared, 1 minus 4t. I care about when does that equal 0, at t equals 1, and at t equals 1/4. So this one's going to have a maximum not at 3/4, but at 1/4. And it's going to have, oh, I didn't actually draw a maximum there. And it's going to have another horizontal tangent at t equals 1. We're going to pass through this point. There's no possibility of a turnaround. Is this a local minimum? I try plugging in a number bigger than 1. If I plug in 2, I get a positive and a negative cubed. I'm going to be negative after that. Okay. So I got a bunch of points that are relevant. It looks like t equals 0, t equals 3/4, and t equals 1, and t equals 1/4 are relevant points for our graph, where either we pass through an x-axis or a y-axis, or we turn around, either in the x direction or the y direction. Let's think about graphing these. Let's start with t equals 0. T equals 0, I get the point, x equals 0, y equals 0. So we pass through the origin at t equals 0. What were we doing before that? Before that point, x was negative and y was negative. X was negative and y was negative. So I must have approached that point from quadrant 4, right? Right. Was I approaching like this or approaching like this? I don't know. That's a thing we could use some derivatives to work out. For now, though, I'm just going to do it like that. What happens next? Our next point of interest is t equals 1/4. At t equals 1/4, I haven't plugged in either of these numbers. X of 1/4 is 1/4 cubed is 1 over 64 times 3/4. I get 3 over 128? No, 256. Ooh, that's a tiny number. 3 over 256 is our x coordinate. What's our y coordinate at 1/4? It'll be 1/4 times 1 minus that cubed, 3/4 cubed. On bottom I'm getting 4 to the 4 is 256 again. And on top I'm getting 3 cubed is 27. So our y value is much higher. I'm probably going to need those same numbers again. Let's put 3 over 256 here. And let's put 27 over 256 here. This is not to scale. I'm not going to try and work this out. So what was significant about the value t equals 1/4? The significant thing was this is the biggest y gets before it turns around. So I'm guessing we were sort of increasing steeply. Our x was increasing that whole time. It increases straight through 1/4. So I keep moving left to right as t increases past 1/4. But our y value hits a maximum of 27 over 256 as our x values keep increasing. Cool. What happens after that? Our next point of interest, we might do 1/2 just because there's a good chance some kind of symmetry is happening at 1/2. But I'm not going to. What's happening at y equals 3/4? Or at the value at t equals 3/4? X of 3/4 is 3/4 cubed. 1 minus 3/4 is 1/4. This is 27 over 256. What's y of 3/4? It's 3/4 times 1 minus 3/4 is 1/4. Cubed is 3 over 256. I get the same point, but with reversed coordinates. So let's label this 27 over 256 and label this 3 over 256. And we're going to hit this point. We're going to go up here. We're going to come around here and then turn around with our x values switch from increasing to decreasing at 3/4, while our y values continue decreasing down to 0. Cool. Cool. What happens after that at t equals 1? X of 1 is 0, y of 1 is 0. So we're going to pass back through 0, 0 again. What happens after that point? After that point, the x is negative and the y is negative, so I'm going to end up over here. I'm getting something like that. These curves might cross each other again. I could ask if the x-coordinate ever equals the y-coordinate again. I'm not sure if they do. But yeah, I get a graph something like this. I have the places where it hits the x-axis at least. And I have the places where it, the fact that I have this horizontal tangent here where my x slows down to growing by nothing before it speeds up again makes me think this is going to be a vertical tangent of this curve. And the fact that over here our y values are decreasing, but they decrease at a rate of 0 for a little bit, makes me think we're going down, go completely flat, and then go back down again. If there's a place where both of them have a tangent, then you can't really tell what's going on. Like, all sorts of goofiness can happen if they both have a derivative of 0. That's the places where you have to take a limit to figure out what the function's slope is even doing. Okay, we sketched that. Here's a question. What's this area? We know how to find slopes and second derivatives and things. Those are much easier. I want to ask, what's this area? I suspect that it's the integral from 0 to 1 of y dx. Let me copy these graphs over to the next page. Before I just compute the integral from 0 to 1 of y dx, I want to sort of think about what's going on. Are these things being positive and negative? Do I need to switch the signs on some chunks or other chunks? Let's try and visualize this. What am I going to get if I just compute integral of y dx on these parts? Figure out when does dx switch from positive to negative? We already did. It's at 3/4. When does y switch from positive to negative? It looks like y is always positive, so that's not going to be an issue. So let's think about the integral from 0 to 3/4 of y dx dt. What's the integral from 0 to, or 3/4 to 1 of y dx dt? 0 to 3/4 was 1/4 down to 3/4 is going to be this chunk. I'm skipping over the 1/4 part because y doesn't change its sign and x doesn't change its sign. So I'm getting this part of the graph if I go from 0 to 3/4. On this chunk, y is positive. And on this chunk, dx dt is positive. So, like, my x things are increasing. I'm on this chunk of time where x is increasing. So this thing is positive. And I'm on y is always positive. So I'm getting this area, but positive. I don't want that whole area. I'm going to want to subtract some of it off. Let's see what happens if I go from 3/4 to 1. Actually, I just didn't mean to draw the whole thing. 3/4 to 1 is, ignore this part. We're only considering this part. On this region, y is positive, but dx dt is negative. So I'm going to end up with this area, the area the y values times the dx values, but it's going to be negative. Oh, sweet. So if I smush these two things together and just integrate from 0 to 1, y dx dt, I'm going to get this area but positive. I'm going to get that area but negative. Subtracting this area off of there is going to give me the area of one full loop, and positive. This happens a lot when you do these problems, where just integrate the thing from the start to the end, and the things you want to cancel out do cancel out, and everything is perfect. It doesn't always happen. Sort of, there's issues about, does your loop turn around on itself? Does it spin around so it's positive on part and negative on part? Those things are not clear. This one was easy, though. So you compute this integral. I'm not actually going to compute this integral. The things involved are polynomials. Y is a polynomial. Dx dt is a polynomial. You'll need to FOIL some stuff out to integrate it, or maybe there's a clever substitution you can do. But the integral's not very interesting, so I'm going to skip that part. But it'll give you this area. The area should be very small, because this all fits in a 27 256ths by 27 256ths square. So it'll be a very small area, whatever it is. There's an example of area in parametric coordinates. It's tricky. Sketching these graphs is tricky. Let's move on to the next section. The next section is about polar coordinates. Have you heard of polar coordinates before? They're great. The key thing going on with polar coordinates is, you know how we specify a point? This point is 3, 2 because you move 1, 2, 3 this way and you move 2 that way. That you go that way by 3 and you go that way by 2, and that lands you at 3, 2. That's one way of turning a point into numbers. That's one way of making a coordinate system out of the plane. The story, it's called the Cartesian plane because René Descartes was sick in bed, and it was olden times where being sick might mean you die. I guess sick people still die. But he was like in bed, staring at the ceiling, and there was, I guess, a fly on the ceiling. And he was thinking about how, you know, I could, to say where the fly is needs 2 numbers. Like, that's sort of a deep idea, that you express a plane by 2 numbers. It's a 2-dimensional object, so you need 2 numbers. Well, polar coordinates are, what if that ceiling wasn't a rectangle? What if it was circular? A much more sensible way of saying the 2 numbers that you need to understand to get to a point, at least in some senses, are to reach that fly, tell me which direction should I face, tell me an angle, and tell me how far I need to go. Give me a distance, r. And that specifies a point r, theta. This point r, theta. Okay, the traditions around this are weird. Which letter goes first, the r or the theta? Almost always, when I write an equation about r and theta, I'm going to think of r as a function of theta, so it makes sense to think of the r as the y value and the theta as the x value, except nobody does that. All the books I've seen put it r, theta instead of theta, r. I'm going to try and avoid doing those. If you can't tell, the theta is probably the one that's a multiple of pi. So that is usually a giveaway. But life is a hassle. So be aware that just because I'm doing it one way, other people will do it other ways, and it just sucks. I mean, it's not that bad. So I will specify a point in the plane by saying let theta be the angle to that point in standard orientation, and let r be the distance you travel to get to that point. So like, for example, if I wanted to go to the point 2, 2 in Cartesian coordinates, what would that be in polar coordinates? 1, 2, 1, 2, doom, doom. How would I specify that? My theta value, oh, I can do that. Theta is going to be pi over 4. What's my r value going to be? R is the length of that line segment is, I do a little bit of Pythagorean theorem, 2 squared plus, r squared is 2 squared plus 2 squared. I get r is the square root of 8, that's 2 root 2. Cool. I can represent this point with theta equals pi over 4, comma r equals 2 root 2. I'd like to put this as an ordered pair, but I never know which letter to put first, so I'm usually going to write it like this. It's worth keeping in mind, though, that that's not the only way to do it. I could have gone r equals 2 root 2, and theta equals negative 7 pi over 4. That'll take me to the same point. If I say go this way by negative 7 pi over, like turn to the right most of 2 turns, and walk forward the same distance, that'll get you there also. This is a downside. Is it a downside? I guess it's probably a downside that coordinates don't have a unique representation in polar. There's only one way of expressing 2, 2 in Cartesian coordinates. The x coordinate's always going to be 2, the y coordinate's always going to be 2. Not so with polar coordinates. You can express the same thing in multiple ways. You can even do this. Your r values are allowed to go negative. I can say let theta be negative 3 pi over 4, and then let r be negative 2 root 2. Rotate to the right 3